seminar in quantitative finance at the Fields Institute on this very spooky occasion, Halloween Eve. Before announcing our speaker, I'd like to first of all thank our sponsors, Scotiabank through the Center for Financial Industries, as well as Waterfront International for their continuous support of this seminar series and other activities in financial math at the Fields Institute. So our speaker today, Professor Martin Larsson, is a professor in the Department of Mathematical Sciences at Carnegie Mellon University. Prior to joining CMU in 2019, he was an assistant professor of mathematical finance at the Department of Mathematics at ETH Zurich. Martin's research focuses on mathematical finance, probability theory, stochastic analysis, and statistics. And if you're interested in that very last item there, statistics, he's giving another seminar in the Department of Statistical Sciences tomorrow and over at 700 University if you're interested. Martin was a plenary speaker at the SCI Mathematical Finance Biennial Conference last year in Philadelphia. And today, let's welcome Martin to share his insights on large-scale dynamics of equity markets of variable size. Martin, the floor is yours.
Thank you very much. Can everybody hear me? I think I turned this on, but just want to make sure. Can you guys hear me? Okay, great. Thanks a lot for that introduction. It's really a pleasure to be here. I'm from Carnegie Mellon, and I just learned now, one of the faculty members here in the department is a former Carnegie Mellon PhD, and I learned today that some of the people in here just spent 6 hours in class with this CMU person who's now a Toronto person, and you guys get to listen for another 45, 50, 60 minutes to a CMU person, and if that wasn't enough, there's an opportunity tomorrow in the statistics seminar to listen for another hour or so to CMU people. So this is really, my condolences. Okay, so anyway, the talk here is joint work with David Itkin, who is one of my former PhD students. David was a postdoc at Empirical in London until this August and is now a faculty member at the London School of Economics. And Li Cheng Zhang, he's a current PhD student at CMU. And the work here is about trying to understand some things about large equity markets. And in particular, we're taking this view that we'd like to not so much focus on individual equities and how they behave, but rather look at the large scale behavior of the entire universe or some large subuniverse of the equities that are out there. Let's see if we can get this to work. Okay, so what I'm going to do is I'll start by just introducing this a little bit. And in particular, I want to talk about this thing called stochastic portfolio theory. This is a theory that's been around for some time, and it is the framework within which we would like to ask the questions we're asking and analyze them. And so I will give just say a few words about what that is and what the basic setup looks like. And then what I'll do is I'll talk about one of the basic models that people have studied in this theory of stochastic portfolio theory, and say something about how you calibrate that model to data. And I'm doing that because I'd like to use the outcome of that calibration exercise to highlight some problems with the way these models are usually set up and how they work. And the focus here is going to be on exactly this issue that when we consider a large universe of equities, or really, many different types of assets in general, but we're focusing on equities here, it is important to not only be aware of the fact that the collection of equities out there changes over time, but also account for that in the right way when you do modeling and when you do calibration and statistics. So we'll see kind of what that entails in the setting of the Atlas model. And then, so I'll show some pictures and kind of try to try to focus on one particular phenomenon that turned out to be critical when you try to estimate these models. And then I'll say something about how the behavior that you see can actually be explained by looking at some very, very simple diffusion-based models for these systems. So that's the plan. And if you have questions during the talk, definitely don't hesitate to stop me and ask if something is unclear. Okay, so we'll talk a little bit about stochastic portfolio theory. And this is a theory that was introduced in the late 90s. Bob Fernholz did this, and it is a framework for understanding the dynamics of equities in a setting where you have lots of stocks, and oftentimes you are interested in looking at these stocks over long time horizons, and you're trying to look at investment. You can think of three kind of main problems that this theory has at least historically tried to address. And the first one is to build models that reproduce the distribution of capital in large equity markets. I'll try to make that statement a little bit more concrete in a second, but it's about model building. These models in this theory, they are not fundamental. They are not meant to be based on economic fundamentals, but they are statistical models, much like you would build a time series model, an arch model, or Garch model, or something like that. They are models that are designed to capture and reproduce various statistical patterns that you see in the data, but they're not intended to, let's say, model investor preferences or model firm fundamentals or anything like that. So that's the type of modeling that goes on here. And the second thing is to think about and analyze trading strategies that take advantage of the stability of the stable quantities that people have identified in the data, ideally without being too model specific. And then there's this third point about relative arbitrage and outperformance. That's going to be completely irrelevant for the talk here, so we can forget about that. Now, the literature in this area is, the vast majority of it is theoretical. It's a mathematical literature that has some very, very nice things going on related to interacting particle systems and other things. But there's not all that much, in comparison, not all that much empirical work that's been done within this framework. That seems to be changing to some extent. So there's some work going back a little bit further, but most of the empirical work related to this has been popping up fairly recently. And in particular, there are people here in Toronto, Leonard, who I think is, Leonard has been working on that together with some students, and they've been doing some really, really nice work more on the empirical side of this as well. And there's more of this that is popping up. What we're trying to do here is to try to contribute a little bit to that most empirical aspects of all this. Okay. So my goal here is to primarily highlight some, I'm trying to be fairly narrow in what I'm focusing on, but it's going to be empirics or some things we see in the data. But I'm going to do this within a modeling framework, so I'm going to have to introduce that framework. And it's not all that much to do. So what we're doing here, and this is the standard setup. You have some equity universe, you have capital N stocks. The market capitalizations of those stocks are called S sub I. That's the capitalization of the stock. I is the name of the stock. Think of it as a ticker. And X, I'm going to use capital X to denote the log cap. That's usually a more convenient quantity to work with. And one thing that turns out to be very useful to do is to rank these stocks from the largest to the smallest according to their market capitalization. And the reason is that if you do this, you start to see some patterns that you maybe wouldn't have seen otherwise. That raises the question of how to connect the rank of a stock, which would be, let's say, 1 if you're the largest, and 2 if you're the second largest, and so on, to the name of the stock that currently occupies that rank. And I'm just going to say rank sub I of t, that is the rank of stock I. If I is Apple, then rank sub I of t is the rank that Apple occupies within the universe of stocks. Okay, so we'll use that notation. Okay, so this is a picture that every time you see talk on stochastic portfolio theory, you will see this picture. So we're going to try to look at some other pictures, but this is a good place to start, just to get one sense of what this is about. So you can compute the market weights of your stocks, or the relative market capitalizations, call those mu, and mu is just the fraction of the overall market capitalization that in this case, the kth largest stock accounts for, right? And the largest stock may account for around 10%, maybe, give or take, of the overall market capitalization. And as you go down the ranks, those numbers will be smaller because they have to add up to 1. And if you do so now at each point in time, you can compute all these weights. So if I do this today, I get some weights. If I do it tomorrow, I get different weights, and so forth. So I can compute those weights. But let me take a snapshot in time. And so, for example, let me pick, for example, this curve right here, the rightmost blue curve. That corresponds to a certain date, namely December 31, 2020. And the curve itself plots the weight against the rank. Okay, and this is plotted on a log-log scale here. That's what the figure is. And you can draw one of these curves for every point in time, right? So you get all these curves. And the observation that was used as the basic motivation for a lot of the things that was done on the theory side of stochastic portfolio theory was that, if you look at these dates here, they go back all the way back to 1925, and 1950, 1975, 2000. And apart from the rightmost tail here, they don't change all that much. Right? There's some changes over time, but those changes are fairly minor. There's not all that much happening, and so these are stable. And that means that this is something that you might hope to be able to model. And it also sort of suggests that maybe there's some mean reversion going on here. And it suggests that maybe if there's mean reversion going on, you'd like to be able to somehow express a view on that, perhaps, right? And so that's the basic motivation where this theory is trying to do those things. Okay. All right. And so this stability of the capital distribution curve, and then there are a few other observations that people have made. Those few observations have motivated the vast majority of what's been done in stochastic portfolio theory. But of course, this is very special. There are a lot of things you can do, a lot of things you can look at. So just focusing on these few things, you're neglecting a lot of other phenomena that may be of practical interest and maybe of intellectual interest as well. And I want to sort of advertise this paper that Leonard has written together with his students, where they've gone beyond looking at just the capital distribution curve and these additional few empirical quantities, and done a much more comprehensive study of very stylized facts that you see when you start to study the data. It suggests many interesting problems to work on, and it's just a really nice paper. And what I want to do today is I want to just focus on one very, very specific thing that's going on that is neglected, believe it or not, in most of the theoretical literature on this, which is the impact that listings and delistings have on what's going on. Okay, so there will be stocks that enter, that appear. There's an IPO maybe or something like that. There will be stocks that disappear for various reasons. They maybe were taken private, or they defaulted, or something else happened. There were mergers and things like this. It's not that people don't know that this happens, but it's an effect that has been ignored largely, because maybe that's not the most important thing that's going on. Maybe there's a lot of things you can say without explicitly accounting for this. That may be fair, because you can't account for everything, but what we're going to do is to look at some very concrete things that happen when you do this. Okay, and here's just a little note about the data that we're using. We're going to use CRSP data. This is just standard equity data set over a 40-year period, and there's some pre-processing going on where the data has to be cleaned a bit and so forth. And there's kind of becoming more standard code for doing that in this context, and so that is good, because this is something that is available freely and makes things more replicable. Okay. All right, so now I want to sort of show what we're doing here and give some context. I'd like to walk you through the most basic type of model that people have studied in stochastic portfolio theory, and it's called the Atlas model. And I want to talk about how that model can be calibrated. Okay. So the Atlas model here is, again, a statistical model for the evolution of the stocks that we're looking at, capital N of them. And the model postulates that the logarithmic capitalizations evolve according to this rank-based model. I'm going to take this stick here and try to see if I can point here. So now let's try to parse this. What this says is that the ith stock here, that could be Apple, if Apple currently occupies rank 1, it's the largest, then it's going to have a growth rate gamma 1, and it's going to have a volatility sigma 1. And if whenever it occupies the second largest position in the market, it's going to have a growth rate gamma 2 and a volatility gamma 2. Okay, so the parameters of the model here, they tell you what your growth rate and volatility are going to be if you're currently occupying rank K in the market. Right? That's how this works. All right, and the main kind of toy example of this type of model is the following. It's a model where you set all of the growth rates equal to 0, except if you're the smallest stock, then your growth rate is going to be some large number. Okay, and this smallest stock, this is sort of where this Atlas moniker comes from. The smallest stock, the Atlas stock. The idea is that it simulates the effect of all the stocks below you. If there are lots of stocks below you in rank, there's going to be some of them, their effect altogether will be this upward push. That's kind of the idea here. And this is obviously a very, very stylized kind of model, and this is not going to give fully realistic behavior. But what's interesting is that if you calibrate the full Atlas model to data, you will see something like this happening. And we'll look at that. Okay. So we said that the ranked log caps are important, and you can write down their evolution as well. And now the growth rate of the kth largest stock will be gamma k, and the volatility of the kth largest stock will be sigma k. That was sort of the point of these parameters. That makes sense. But then there's this term at the end, which is 1/4, and then there's some lambdas. These lambdas are known as local times, but what they do is they quantify how much turnover there is at rank K. So in other words, what is the intensity of switching at, let's say, rank 2 of between different names. So there'll be different names will occupy rank 2 at different times, and how often does that switch? That is what this thing measures. Financially, the way to think about it is the following. Let's say that you try to hold the largest stock. You want to hold the largest stock. All right, so you buy the stock that's currently the largest. But now you wait, and eventually that stock will no longer be the largest, because whatever was previously the second largest will have overtaken the guy you bought. So now you have to sell the guy you bought and buy the one who's become the largest. The problem when you do that is that right after the switch happens, your stock is worth a little bit less than the one who became the largest. So you have to sell low and buy high. So you lose a little bit. And now maybe they switch back a little bit later, and you have to do the same thing again, and you still lose a little bit. And the lambdas here, they quantify how much you lose if you try to do this. So that's kind of a good way to think about these lambdas. The same type of thing happens if you're trying to hold the largest 10 or the largest 100. As soon as one stock drops out of the group that you would like to hold, you have to sell it and buy the one that entered into the group you'd like to hold, and you lose a little bit when that happens. And that's what this lambda quantifies. So they are important quantities. They measure this. It's often called leakage cost of this kind of portfolio. Okay. Now, so this model has some nice properties, and there's a certain stability condition here. I think I won't talk too much about it. It's a very intuitive thing, which says that the average growth rate of the entire universe, if that average growth rate of the entire universe is always higher than the average growth rate of, let's say, the top 10, the top 11, the top 12, then the whole population of log cabs will be kept together, and the system will be stable over time. And what that means specifically is that if you look at the log cabs and you subtract off their average, then you'll get something that is an ergodic process. Think about it as a stationary process. So that's what happens in this model, and that's a very useful fact. And in particular, it leads to there's a now third set of parameters. We had the volatility and the growth rate, but we now get another set of parameters that comes out of this, which is, I'm going to call them little lambda, and those are the average collision rates. So that is just over time, if you insist on always holding the top stock only, what is the average leakage cost that you're going to pay over time in the long run? Okay, that's what the lambda measures, and that is going to be a number under these conditions, and that's an additional parameter. It's implied by the other parameters. It's not a free parameter, but it's useful to look at it because that fact allows you to calibrate the model. All right, if you want to calibrate volatilities, you can in principle do it by looking at realized variances. This is a straightforward thing, and you can do that. If you like to calibrate the growth rates, that's impossible, because you have a very, very poor signal to noise ratio in these situations. So you can never get direct estimates of the growth rates that are reliable. That's impossible. But the lambdas, those can be estimated reliably from data. And because of the stability of this model, it turns out that there's a direct connection between the growth rates and the average collision rates. So if you can estimate the lambdas here from the data, then you can use this relation to back out the drift parameters. Okay. And so in particular, I want to just mention one consequence of this relation here, which is that the growth rate of the smallest stock in this model is essentially going to be the same as the average collision rate of the smallest stock, let's say. Okay. And I'm gonna show you what these come out to be when you calibrate this model, and that'll give us some idea of what this guy is gonna have to be, the growth rate of that smallest stock in this model. Okay, so let's look at some pictures. These are the calibrated volatilities in the Atlas model, and here there is a blue curve. That's just a plain average, realized volatility estimator. And then there's clearly some pattern here. So there's a less irregular line, which is a smooth version of the blue line. And you can see here that volatilities are low at the top, and then they increase as you look at stocks occupying smaller and smaller ranks. Low-ranked stocks tend to have higher volatility than high-ranked stocks. That's a well-known thing. And this is what it looks like if you estimate based on the data we have. What about the collisions? Okay, looks like this. So what does this mean? Well, it means that at the top here, the very largest stocks, there isn't all that much turnover. But when you go to lower ranks, very small cap, 2,500 and so on, the amount of turnover, amount of switching grows dramatically. It just grows and grows and grows and grows. By the way, this curve isn't exactly monotonic. It is a little wiggly if you zoom in, but it definitely looks very monotonic at this scale.
Sorry, Martin,
yeah.
Question. How should I interpret the units of this measure? What does 1,000 mean versus?
Maybe a discussion for afterwards. It's not super easy to, right? Because we're talking about log caps here, and so if I want to interpret these as leakage cost, then if I did the leakage, if I did these collisions on the caps themselves, it would be sort of, I could have a dollar unit, so it'd be sort of amount of money I lose on some normalized portfolio. Now I'm doing this on logs, so there is a multiplicative, let's say the logarithmic multiplicative gain or loss but it's a little tricky with exactly how to interpret the units. But so the y-axis here, I'm putting it in because later on, I'm going to tell you later on, this curve is actually completely wrong. And one way I can show you that it's completely wrong is because the numbers here will be completely different for the correct curve. And that will allow me to compare them. But it's not straightforward to get a clear interpretation of what the number in isolation actually means. So, okay. So, all right. So what is wrong with this? I just said it was wrong, right? So what's the problem? And the problem is that, you look at this, it just keeps growing and it's accelerating. And when do we have large collision? When do we have high collision rates? We have high collision rates when there's high volatility. If there's high volatility, you expect there to be more turnover. If there's high called particle density, meaning that there are a lot of stocks that have similar log caps, it's more likely that there will be switchings, and that will contribute to higher collision rates. If there's very low correlation between adjacent stocks, you would also see more switchings. The way to see that maybe is that if you have perfectly correlated particles, they will kind of just move in tandem like this. There's no collisions. They just move together. But if they're low correlation, then the opposite happens. Now, if I go back, it's plausible that for smaller stocks, just say, for smaller stocks, it would be denser and more volatile. But that cannot explain this very, very rapid growth, especially if you try to extrapolate going out. Can't explain it. So there's something else going on here, and we want to try to understand what that is. There was a question.
Oh, this is end of day kind of question, you know. So you gave an example if they're positively correlated. I imagine if there many things are negatively correlated, they'd flip around like low
Yeah, so
regularity.
you could imagine that there's some negative correlation among, but that's not something you would expect to happen much.
Okay.
Basically because they can't really all be negatively correlated with each other, right? You could have in some places maybe that there's no, but we're going to see some estimates of this as well, and they're not negative typically. Yeah. Okay, so if you sit down and think about what causes this big increase in collision rates, and it's not really clear, how can it be that the collision rates are just so high, just keep growing and growing and growing even as you expand the universe of stocks. And now this paper that I advertised in the beginning, one thing that they show here is that listings and delistings are important for various things that go on. And they are important drivers, for example, of the stability that we see in the capital distribution curve. And what we'll see is that actually listings and delistings, they also affect these collisions in a critical way. And I have a little cartoon here to try to illustrate what goes on. And look at this. Look at this. We have the largest stock, goes like this. We have the second largest stock, goes like this, that's a black line, third largest, fourth largest. But then let's say at some point in time, there's a listing event. So new stock pops up here. Now this guy is the second largest. What happens to the capitalization of the second largest stock? Well, it goes from here just before the listing event to here just after the listing event. So there's a positive jump in that capitalization. And this leads to jump in the third largest capitalization as well, because this guy was the third largest, but afterwards it's the fourth largest. And the capitalization of the third largest jumps to here. So they all jump. And this all feeds into the estimates for the collision rates and make them huge. Delistings will have a similar effect, but opposed. And overall, these effects lead to very, very large collision rates. So we want to try to see if we can account for this in some way and see what happens then. So I'm going to just take a look at what these capitalizations actually look like. And I want to try to just in particular show you some listing and delisting events here. And so what this is on the x-axis here in the top plot, you will have the centered logarithmic capitalizations. It's a histogram of those. The red bars here are indicating where the 100th largest stock is, the 500th largest, and so forth. And at the bottom, we have a histogram showing listings and delistings at different centered log caps. And you can kind of see what this looks like over time. And this thing moves over time, and you can see that these red bars, they move a little bit back and forth, but not all that much. And that's indicative of the stability of the capital distribution curve that we saw before. But you can see that there's a lot of activity here. The listings and delistings, there's quite a bit of those. And it's plausible that this, because the cartoon I just showed you, it's plausible that they might have a significant effect. So let's look at that. Okay. So now what we're going to do is we're going to have a listing date or birth date beta I and a delisting date or death date delta I for each stock. And the capitalizations will only be defined between those dates. Okay. You can count at any point in time how many stocks you have in total. That number will vary. We're going to assume here that we always have at least one stock and that this thing doesn't blow up and stuff like that. There are some papers where people have studied markets of variable size they don't really have much bearing on what I'm talking about here, but people have looked at this. I can define trading strategies in a very simple way in this setting. I won't talk too much about that. But what happens now is that even though my capitalizations themselves, well, they start to exist, and then they move continuously in the model we have here, and then they disappear at some point. But when I rank them, I will start to see jumps. And exactly because of this cartoon that I showed you. So there will be these jumps that occur whenever a stock is listed or delisted. Now, I didn't say really anything about how exactly we estimate the collisions in the standard model, but using the framework here with listings and delistings, I can fairly easily derive an analogous estimator where I account for listings and delistings. And I can, in particular, I can also include stocks that only, I can include ranks where there was only anyone occupying that rank for some sub period of my sample. I couldn't do that before. So I can do that now, and this ought to hopefully fix the problem that we saw before. Volatilities and correlations I can estimate. That's not really a big problem. I can still do that by looking at realized volatilities and realized correlations. Okay, so now what we're going to do here is we're going to take data over time horizon, and that's going to be these 40 years of data that we have, and we can find estimates of our collision parameters, volatilities, and correlations by looking at realized quantities or by using this estimator of collisions that I alluded to. And what I'm going to do is I'm going to plot this normalized quantity. This is the collision rates normalized by variance and also by correlation. And the reason I'm doing this is that, again, if there's a lot of variance, then I expect then that will cause a larger collision rate. And if correlation is, let's say, very high, then that will cause a lower collision rate. So by normalizing these in this way, I standardize these quantities to account for that. And I'm going to compare that to a second quantity, which is a proxy for particle density. I said that if we have high particle density, we ought to also have higher collision rates. So we're going to compare those two. And there are various ways you could define this. And we're doing something simple here where you look at a particular rank K, I look at at plus minus 5 ranks. I look at that distance, 1 over it, and I look at the time average. That's kind of what we're doing here. All right. I want to compare these quantities. And okay, so let's first look at the volatilities. So this looks at the same way it did before. Essentially, it's just that before I had to cut the plot somewhere here because after that, I only had stocks occupying those ranks for some sub-period. So I didn't know how to do that before. But we see that this kind of continues. At the very bottom here, it goes a bit haywire. That's because we have very little data at this very, very low ranks. Above 7,000 is just very small part of the time period that I really have stocks there. But this looks reasonable. Here's a plot of the correlations. And this comes back to the question earlier about sign of the correlations. And you see that at the high ranks, they tend to be more correlated with their neighbors than at lower ranks. And find there's some negative values here, but this is noise, right? And so we have that. And here is the the corrected collisions. So we can see that it still grows, and this sort of makes sense. We have a denser population of stocks around, going down the ranks down to 1,000, 2,000, 3,000, and so forth. Then down here, things start to look much less clear, where we don't even have stocks at these low ranks for part of the time. And if you go all the way down here, then this is going to start to come down again because down here just aren't any stocks, there are no collisions, right? And now we're going to look at the particle density that we want to compare this curve to. And it looks like this. Okay, so these two look pretty similar qualitatively in their shape. And so that is giving us some confidence that we're now estimating these collisions much in a more correct way than we did before. Now you see here that okay. So now we're coming back to our question of what's the y-axis here. I'm not going to try to interpret it, but I'm just going to compare the numbers here to what I would get if I did this for the original model. Now these are variance normalized. So I have to plot the variance normalized version of the plot I had before, and that's this. Okay, and so now, you know, this goes from 0 up to 5,000 or something like that. Again, I can't go all the way out to, I have to keep looking at ranks where I have data in the whole sample. And so here around 3,000, I'm up at 5,000. And over here at 3,000, I'm up at about 1,000. So it's a really big difference. And the shape of that particle is just completely different. So it's just you know, this is completely wrong. This is completely wrong. Okay. Okay, so the curves that I showed now, these are based on time averages, right? Average of the entire 40-year sample period. But things don't look exactly the same. This is not a stationary system. We have business cycles, and there are crises events, and there are all sorts of things happening, bubbles and other things. And so what I want to do now is to look at what happens when I do this analysis but I average over 1 year chunks, okay? And I look at how these curves that I plotted here change as I go from 1 year to the next. So let's try to do that. And I'm going to go to this here. So now where we're starting here is the 1 year period from 1980, well, the year of 1984. And I'm looking at the variance normalized collision. That is the blue curve in the back. And I'm looking at the particle density. That is a red curve. Now, they overlap exactly, but the blue curve, the y-axis is on the left, and the red curve is the y-axis on the right, just so that you kind of, it's not the same number, but the shape looks the same. And then over here, the correlations are plotted. I want to focus on the left part of the curve. So we can take a look at how these develop over time. And you see, you know, they track each other reasonably well for most of the time, but not always. And you'll see that there are going to be examples, periods of time where they depart from each other, right? So you see this, the blue curve, we show the variance normalized collisions. They it starts to overshoot sometimes, and you'll see that, for example, in the COVID years and so forth, that you have this kind of behavior. So there are some things here we still don't quite understand, but for large portions of the sample period, these line up fairly well. So let's try to understand if this is something that we should expect, this kind of a qualitative agreement between particle density and normalized collision rates. Okay, so the way we try to understand this is by looking at a model that we call the local model. And what we're going to do is we're going to zoom in on one particular rank. So I'm going to look at, for example, the 1,000th largest stock. So I pick 1,000, that's my rank. And what I want to do is I want to just model that one stock and its immediate environment. I don't want to try to model all the stocks in one go, but that one stock and its local environment. And I'm going to do that by considering a Ornstein-Uhlenbeck process, mean reverting diffusion, where I sort of have this somewhat funny indexing, but so I have 2m+1 particles, and I'm going to index them from -m to m. okay? And they will all have the volatility corresponding, which is the volatility I estimated for my 1,000th largest stock. They will all be correlated. They will all be driven by Brownian motions that are correlated with rho, all the same, all symmetric. And that rho is the correlation parameter that I estimated for the 1,000th largest stock. And I'm setting this up so that I get a stationary process that allows me to look at these long-term time average quantities, and I get things that are stable. And so what I'm going to do now is I'm going to look at the median particle in this system. And I'm going to view that median particle as a model for the kth largest stock that I'm interested in. And I'm going to look at all the other particles in this system as the stocks in the immediate surrounding of the kth largest stock. That's the plan. And so if I look at the order statistics here of the y's, then I set this up so that y sub bracket 0 here is my median particle. That's kind of what I did. That's the one in the middle of the sample. And I can look at the local time of this gap. This is exactly the analog of the collision local time that we saw before. And I can look at the time average of that. That will have a deterministic limit in the setup. And I can also look at the average particle density. That will also have a long-term limit in the setting. And we can, and it turns out now that if I look at the ratio between the particle density and my variance and correlation adjusted collision rate, then this is about 2.2. And this will actually be pretty insensitive to what M is. M could be 20 or 30 or something like that. It's not too important what M is. It should not be 1 and probably not 2. It doesn't have to be 10,000, but 50 maybe or something like that. And we'll have 2.2 here. And if you look again at the plots that we had, and let me, well, this is not too bad. You will see that these lines, they roughly overlap, right? So the ratio between the two quantities is more or less the same. And that ratio will be, that number divided by that number, which is about 2. And that agrees pretty well. Now, there's noise here, and there are things we're not adjusting for in this setting, but that agrees pretty well with this predicted value of 2.2 that you get out of the very simple diffusion approximation for this local environment of the kth particle. Okay. And so what we take away from that is that, as a baseline description of the fluctuations of the log capitalization at the fixed rank, this kind of diffusion model is reasonable. And if you want to do better, you at least have to outperform this. Okay. Just for fun, we can you can plot some trajectories here. Each curve here this is a 2-year time interval, and each curve corresponds to a different 2-year period during our sample. And now in one plot, we have the 2-year trajectories for the stock that was ranked 500. Okay, so it's all ranked 500. It's just different 2-year chunks. And here we have simulated trajectories of the median particle in the OU system, where we've kind of calibrated things so that it lines up. I think this is the actual data, and this is the simulated data. Could be the opposite, maybe. I don't know. It's a little hard to tell. But here is the 2000, the same for rank 2000. And so, no, I'm just joking. This is the actual data at the top. But you know, and you can kind of tell, right? But they're pretty similar, right? Just kind of eyeballing trajectories, which I know is kind of unscientific, but you know, we have to start somewhere. Okay. So I think I will skip this. I had just one slide on this. So what I'm going to do is skip that and just conclude. So you know, we have this framework, stochastic portfolio theory, which has been around for 25 years. And this has really generated a lot of really interesting research in mathematics. But there hasn't been all that much on the empirical side. But now we're starting to see more of that. And there's some really interesting phenomena that one can look at, and that also can be modeled. You know, sometimes it's difficult to get to in finance to have models that really do well, but some aspects of these systems really seem to be amenable to modeling. You know, what I specifically wanted to highlight in this talk was the role of listings and delistings on some of these quantities that we're trying to estimate. And in particular, you know, we have a framework for varying equity universes. I highlighted this local model, which I think is a useful, very simple baseline for modeling these things. I think it's, you know, it's a good null model that you'd have to beat if you want to do better. And there are a bunch of other things that I didn't really talk about here, but that are of course important. And one thing was the slide I skipped here at the end, a global model. Maybe we do want to model the entire distribution simultaneously, and we'd like to have a way to do that. Factor structure, most of the models in SPT, but not all, but most models, they don't really seriously consider factor structure in returns. There's a lot of idiosyncratic model, you know, idiosyncratic noise only. So that needs to be incorporated in this setting. There's also kind of questions about the statistics of listings and delistings. What is the lifetime distribution of stocks? What is the distribution of entry capitalization? Given that there is a listing, where is it going to be in the capitalization distribution? What is the distribution of volatility? You know, all these things are things that we should model. And then the global model, I didn't really talk about that, but it's a very simple model. But there's still some very kind of interesting and not so trivial mathematical questions that ought to be studied regarding that. So these are things we're kind of working on now, and I think there'll be lots of problems for others to work on too. So thank you.